Okay. If we may begin. Thank you. So, firstly, many apologies for not being here yesterday. It was a great source of pain. I was trapped in mainland Europe on Sunday night, and the storm meant that all flights were cancelled. Indeed, I've had to struggle to get here for today. I tried to persuade Professor Harnew to double up and give 2 lectures yesterday, so I could give you 2 today, but he was not to be persuaded. But still, don't worry, I think we have plenty of time to cover all that we need to cover. Right, so today we discussed the topic of effective potentials, which was something I gave a preview of last week. But let me start from the beginning again, because last week was a while ago. So we have the energy equation that half mr dot squared plus j squared over 2mr squared plus ur, where u of r is the real potential energy. So let's just remember where these terms come from. So this is the kinetic energy, but it's being decomposed into the radial part and the azimuthal part. This is the energy equation for a central force, I remind you, and that enables us to write the azimuthal part in terms of the angular momentum which is conserved. Okay, so you look at that and you say, well, initially we started with a formula which was dependent on 2 dimensions, r and theta. Now it is only dependent on r and r dot. So let's now say, well, let's define a effective potential, which is U effective of R equals J squared over 2mR squared plus U of R. Okay, so just to labour the point again, this second term is, in reality, it's a kinetic energy term to do with the azimuthal motion, but because of the nature of the central potential, we can write it in that form, and now it has no apparent dependence on velocity. It only depends on r, so that encourages us to actually bring it into the potential energy, and we define this effective potential. Okay. So now the problem becomes 1D like. Okay, so we're only dependent on r. So this is nice. So this allows us to predict important features of the motion without actually having to go and solve equations. And in the lecture today we'll do a bit of solving, but we'll also look at forms of effective potential, and we will learn things about the motion just by looking at the form. For starters, if I just let me just write what we have. We have E equals a half mr dot squared plus uf of r. Well, let me do a trivial rearrangement. So just put the half mr dot squared on the left-hand side. And why have I done that? Well, because this is r dot squared, we know that the left-hand side has to be positive, or 0 or positive. So this is always greater or less than 0, and this tells us that the energy, therefore, must always be greater or less than, greater or equal to the effective potential. So we get this statement on the bottom of the slide here. Okay, I just said less than. I've neglected the special case when it's equal to. But it means that if we're considering possible solutions to a problem where motion can occur, motion can only occur for the cases that the effective potential is less than the energy, less than or equal to. Okay, that might sound a bit abstract, but let's again draw, and I do it over here. So I'm going to draw, as I did last time, the effective potential for the case of gravity. Okay. So then we have U of F R equals J squared over 2mr squared minus G big M little m over R. So I'm just going to draw what we have on the slide, but we can quickly do it here just so we understand what's going on. So firstly, if I have the second term, the real potential energy term, that has this form. So that is minus G big M little m over R. But then we have this J squared term here, which is positive and is coming down more rapidly. And then if we superimpose these together, we're going to get something which is comes down, comes below 0, finds a minimum and then goes up. So this is U of F, and this is the J squared over 2mr squared. Okay, so that's what we have sketched here. Now let me repeat this statement here that we require for allowed motion that U of F of R is less than or equal to E for all R. Okay, so this is a requirement. So now we see that the possible motion we get therefore depends on the absolute, on the value of the energy we have. And we're going to have a variety of solutions. So the first solution, again, I'm just repeating this drawing on the slide, but building it up stage by stage. So the first solution is the case where, the sort of generic case where the total energy, okay, let me give this a subscript total so it's clear what we're talking about, where the total energy is less than 0, and I draw this case here, right? So this is case 1. Okay. And we see that this horizontal line intercepts the effective potential in 2 places, okay, which I call R1 and R2. So you're familiar with looking at potential graphs and understanding what the motion is. So as I say, the allowed motion is such that one has to be below this energy. Okay, so anything which is moving in this effective potential, and this is gravity, so it may be a planet, for example, can only move between here and here. Okay, so motion is allowed where the radius of the planet can vary between R and R2. Okay, so this is so So this is describing an orbit. This is clear, and we'll talk a lot more about orbits. But the orbit will have a radius which varies between a small radius and a larger radius. So the orbit is bound. The radius never becomes infinite, but it varies. So this is a bound orbit with r varying between r1 and r2. And looking ahead, we will later study the properties of such an orbit and find out it has to be elliptical, but we won't make any such statement here. Now, another case, which I call case 2, is when we are sitting, just move this up, we are sitting just at the bottom of this potential. This is 2. And let me call this radius here R0. Okay. So in case 2, the E tot is at the minimum of the effective potential, and R is equal to R0. So in this case, the radius, again we're in an orbit, but the radius isn't changing. The radius is just sitting at R0. And you know clearly what sort of orbit that is. This is a circular motion. Okay, so this is the simplest case. Okay. Now there's a third case. Sorry, I have to keep on moving the boards back up and down, but this will be the last time. Third case is when the energy is higher. So the energy is up here. So this is case 3. What do I call this? So here there's an intercept there at R subscript 3. Okay, so in case 3, well, this is interesting because the line is intersecting with the effective potential only in one place. So there is so there seems to be a minimum radius, but there's no maximum radius. The maximum radius is at infinity. So in this case, well, firstly, what is the regime of the energy? The regime of the energy is positive, you see, so we're above the top side of the axis, so this is a positive energy. So here we have an unbound orbit with the radius greater than R3. So these are the 3 cases which are possible, and we will start to consider these in some detail. Just to sort of talk more about this third case where you have an unbound orbit, let me just remind you of something you might have spotted. This was 3 years ago now, where an object was detected flying through the solar system, coming close to the Sun, and from the trajectory of its travel, it was one could calculate that it was in an unbound orbit. That meant it had a total energy greater than 0. So just this case. So this is something which was not orbiting in the solar system, but could only have come from outside the solar system. So this was this object which was given the name of this, which I won't attempt to pronounce. This is an indigenous Hawaiian name, which means something very elaborate. But this was the first known interstellar object to pass through the solar system. Okay, so this was following a hyperbolic trajectory with a velocity starting out there. It could be calculated at 26 kilometers per second. It was speeding up and it will eventually leave the solar system, but in some time. Okay, so these cases, this case and what we will later find out to be the elliptical case, we are going to consider in some detail. And we'll also talk about the gravitational application in some detail. But just to get more familiarity for how the effective potential works, and also to make clear that it isn't just restricted to gravity, now let's consider a couple of other cases. So firstly, the 2D harmonic oscillator. Okay, so this is a. Oh, I put my. Okay, so this is just an object on a spring, which is moving like imagine this is a tabletop. So the thing can move around such like this, and the string can stretch. So it's a two-dimensional problem, x and y. Hooke's law applies, so force is inversely proportional to the extension. Let's solve the problem first by just considering just initially ignoring the natural length. Okay. So this is just a detail, just to make the initial analysis straightforward. So here, initially the radius, this r will actually just relate to the whole length of the spring, but in reality the spring has a natural length, and we're just having to worry about the extension. Okay, so the energy equation in this case. Well, it will, again, will be a half mr dot squared plus uf of r, because once more, this is what is key here, this is a central force, right? This is something which can't be stressed enough. That is what is allowing us to just write uf as j squared over 2mr squared. But now we need, for the potential energy, it's not gravity, we need the potential energy which is in the spring, and that is, as you know, a half kr squared. So this is the true potential energy in the spring. So this is a formula you should know well, but it's easily obtainable by just integrating this over distance. Okay. So firstly, let's just consider the case. Well, firstly, let's. Why don't we just sketch this effective potential? Okay. So I think I can do it here. So once more, actually, we won't need the negative part of the axis. So let's do it. So once more, we're going to have the j squared over 2mr squared bit, which is going to be falling here. This is the j squared over 2mr squared. But then we have the true potential energy, which in this case is going to be just a parabola. So this goes up like this. So this is a half kr squared. So if I superimpose these, I get something which is like that, UF. Okay, let me draw that again because I want to annotate it. And So this is UF, and this is R. So let's, as we did for the gravitational case, let's consider what motion is possible. The only motion is where the total energy is higher than this. So in fact here we just have two cases. So this is one, so this is 1 and 2. So case, so the numbering is maybe not optimal because it's slightly different to here, but case 1 here is when the radius is, when one is sitting at the bottom of this potential. So this is a fixed radius and circular motion just as before. Okay, so you're sitting here and nothing is changing. In case 2, then you have once more a varying radius. But what is key is that it varies between here and here, so the orbit is, the motion is again bound. Okay, so again it's a bound orbit. I'll put it in inverted commas because it's a little strange to consider this motion of this mass on a spring as an orbit, but you know what I mean. What we don't have here is no unbound case, right? Just because of the shape of this potential, wherever I draw this horizontal line, the orbit will always intercept at two places. Okay. So let's just so we've looked at the shape of the effective potential and we've got some insight into the possible motion. So let's consider the circular motion case in more detail. So let's say, well, here it's going to be at the bottom of this potential, so it's defined at dUF by dr equals 0. Okay, so what is dUF by dr? So dUF by dr is going to be given by, so differentiating the form of the potential, which is just at the very top of the board. So I get minus j squared over m r cubed plus kr, and then this is equal to 0 at r equals r0, which is r0 is what I define to be the radius for the circular motion. Let me just annotate my diagram one more time. This is r0. Okay, so what is J? Well, J is the angular momentum. Clearly, as it's clear from this diagram, we start with this velocity v0. So J, and that velocity is entirely azimuthal. There's no radial component. So J is equal to mv0, and it must be r0. That's the radius at which we start as well. So let's, if we substitute this in, what do we get? We get mv0 squared. You get an r0 squared on the top, but you have r to the cubed on the bottom, so that gives you over r0 equals k r0. Okay, so that's that expression makes a lot of sense because this is the centripetal motion, this is the centripetal acceleration, and this is the force provided by the spring. Okay, so this looks sensible. And the actual, okay, to just invert it, the position of the radius then is just going to be given by the square root of m v naught squared over k. So by making a simple analysis of this effective potential, we got a familiar expression, an expression that you could admittedly have probably written down at the start, but it's nice to see that these results are dropping out from this alternative analysis. Let me move to here. As I said, this was just so we could see the wood for the trees. This initial analysis ignored the natural length of the spring. Let's say the spring, let us actually include natural length, just for completeness. Let's say it has a natural length of A, then the force, rather than being minus K of R, will go to force equals minus K R minus A. Okay. And then the actual potential energy, rather than being a half K R squared, that will go to a half K R minus A squared. And then eventually this same analysis will lead you to an expression where mv0 squared over r0 is equal to K R0 minus A. So you can just work, it's just a straightforward generalization of what we've just done, allowing for this offset. So this is the analyzing the case where we have circular motion. What about if we allow for the other case? So case 2, so this is where, this is for higher energy, okay. So let us try and consider what happens here. Well, here, what is obvious is that the radius can vary, so let us try and solve in this case. So for the general motion, we had that F equals minus K of R. So if we turn these into two equations of motion, so this is just a brute force old-fashioned analysis. So mx double dot equals minus kx, my double dot equals minus ky. So this is clearly simple harmonic motion solutions. Let's put in some initial conditions. So initial conditions i at t equals 0. Well, what shall we say? Well, let us say that x is equal to R2. Is it R2? Yes. So R2 is this length here. So let's say we start it at there with y equals 0. And what else do we need? Yeah, let's say we start it with no velocity in this direction. X dot equals 0. And we'll actually need one other piece of information to nail everything. And that other piece of information will be that by the time the object has got around to here, we'll define this length as R1. Okay, so this is just, so this won't be at t equals 0, it's at when when theta equals omega t, where omega is the angular velocity, and that's at 90 degrees or pi over 2. Let's fix that to be R1. Okay, so the purpose of this is just that we clearly have x equals a cosine omega t plus b sine omega t, and y equals c cosine omega t plus d sine omega t, where omega is the square root of k over m, and a, b, c, and d are constants. But with the information I've given you there, we no need to go through this blow by blow. We will tell us that x equals R2 cosine omega t and y equals R1 sine omega t. Okay, so that follows just from the boundary conditions which I've written out. If we look at the form of these solutions, we can see that, okay, if I divide x by R2 and y by R1, we're going to have a cosine omega t and sine omega t, and if we square those, let me just do this. And y over R1 squared equals sine squared omega t. And of course, if I add those, I get 1. So we see that x over R2 squared plus y over R1 squared equals 1. So this is not a circle. What this is an ellipse. Okay, and this is what you might have guessed. And this prefigures what we're going to see when we make the same analysis for the gravitational case. So that's one problem which we solve with the effective potential. Here's another one, which is, again, slightly more elaborate. What's going on here? So we have a tabletop with a hole in the middle, and we have a string which is connecting two masses which are equal, m and m. The string is inextensible, so it doesn't stretch. It's of a length L. We're going to define this length R, which is the length on the tabletop, and this can, of course, vary. And we're going to start it such that R equals L over 2, and it's moving at with a perpendicular velocity v0. Okay? And this is one question we're asking here, but actually we want to make a general analysis of the problem. Right. So in fact, get to my relevant piece of paper. Great. Let me first just ask, before actually trying to find this speed at which the particle below the table falls, let me just first consider what are the conditions for circular motion, just knowing what you knew at A level without actually coming to use the effective potential. So first, what is the condition for circular motion, because this will give us a result which we'll come back to later and check with our more sophisticated means. So let's just here equate forces. So what are the forces? Well, there's the thing on the table will be spinning around in a circular way, so that will have a centripetal force. It's going to be mv squared, but the v is v naught because that's its initial velocity. And the radius it's moving at is L over 2. That's right. And that must be, where is this force being supplied by? It's being supplied by the gravity pulling the mass down. So that equals mg. So this gives v naught squared over gl equals a half, or v naught equals root gl over 2. Okay, so that's a simple result which you could have got while still at school, but we've just made this analysis. Let's store that result away. We're going to come back to that. But now let us turn to trying to answer the question posed here. What is the speed at which the particle below the table falls? And we're dealing with effective potentials, so we're going to analyse the problem in that manner. All right, so the energy equation what components will it have? It's going to have. Okay, so firstly we have this kinetic energy term, the radial kinetic energy term. Again, this is a radial force, a central force. So we have a half m r dot squared. But in this problem, we have something else which is moving, which is relevant, and that's the object below the table. Okay, so we must add here plus a half m y dot squared. Okay, where the y is defined as there. Y equals L minus R, the distance below the table. So this is the kinetic energy. But we still have the azimuthal motion, which for this central force, we as usual, we subsume into the j squared over 2mr squared term. And then there's the true potential energy. This is the true PE. And what is that? That is the potential energy associated with the height of the mass below the table. Okay, so let us say that this u of r, it's just to do with the height of that mass. So let's say that's minus mgy. So it's just a height times the mass times gravity. Let's just sketch this. So with y defined as I have it, then what we have is minus mgl. This is 0. This is L. Okay, so this is u of r. Okay. So the bigger r is, so the bigger r is, then the smaller the amount of string below the table, the higher the mass is. So we expect the potential energy to rise with r as the mass is being pulled up. So that's right, it has the correct gradient. We have the right sign there. Its minimum case would be when r is 0. That's the case where the little mass on top is about to drop through the hole. So this is the minimum case. The actual origin, we see that U is defined to be 0 at y equals 0, which is r equals L. So this is where U is 0, but that definition is arbitrary. Okay, so you can define the potential energy, the origin, to be wherever you want, so don't get hung up on that, and the analysis we will do will not depend on that. Okay, so let me write down again this the total energy then. So it's a half mr dot squared plus a half my dot squared plus j squared over 2m r squared, and then this final term is minus mgy, which is minus mg L minus R. Now, of course, it's going to be interesting and instructive to sketch that, but we'll do that on the next slide. Here, let's just crank on and do the try and do what we've been told, which is to find the speed at which the particle below the table falls. So that is it's related to these terms here, clearly. But firstly, this is the total energy. The energy is conserved. So what is the energy? Do we know the energy at any given time? Well, we do. At t equals 0, we know plenty of things there. We know that, for instance, we know the value of J, because the thing starts at a radius of L over 2. It's moving at some velocity v0 perpendicular to the spring. So J is m v0 L over 2. And therefore, we can write what the energy was at that moment. At that moment, the mass is not falling below the table. The only kinetic energy is associated with with the circular motion of the mass on the table. So it's just a half mv naught squared. And then there's some potential energy because the string below the table is of length L over 2. So we have minus mg L over 2. Okay. So these are things which we know at t equals 0. So we have this energy, and we can now, so we can put this into this equation. From energy conservation. Let's try and do this. So firstly, this on the left-hand side, mv naught squared over 2 minus mg L over 2 equals, and then on the right-hand side, mr dot squared over 2 plus, okay, so then we have my dot squared, but y dot, well, y is no more than L minus R, and R is a constant, so y dot is the same as R dot. Well, y dot is minus R dot, so if we square it, we'll get the same, we'll get another mr dot squared over 2, since y dot equals minus R dot. Okay. Then we have the j squared term, and we know what j is, it's that. So if you put that in, you get m v naught squared L squared over, you get an 8R squared, and then the potential energy term minus mg L minus R. Okay. So we're trying to find the speed at which the thing falls, that's y dot, but in magnitude it's the same as r dot. So we just need to rearrange and solve this for r dot. So we just, it's simple stuff, but let's just do this. Divide through by m, multiply through by 2. We have v naught squared minus gl equals, I get here just an mr dot squared from adding these, but I'm dividing by m, multiplying through by 2. So 2r dot squared plus v naught squared L squared over 4r squared minus 2g L minus r. And then, so the solution is that r dot squared, which is the same as y dot squared, I emphasize again, is going to be given by gl plus v naught squared over 2 minus lv naught all squared over 8r squared minus g of r, minus g multiplied by r, I beg your pardon. Just check that's okay. Right, so we have found the solution. Let's just check this makes sense. What about, so when we start it, we have r equals L over 2. At r equals L over 2, right? So what happens in this case? Well, we then have so this should be a, let's just check it works out. So we have a GL over 2 plus V naught squared over 2 minus, so putting in for this term here, r equals L over 2. I'm going to get L squared on the bottom, but I've got an L squared, V naught squared on top, so I'm just going to be left with a V naught squared. The 2 squared gives me a 4 on top, and I've got an 8 on the bottom, so this is going to give me minus V naught squared over 2, and we end up with minus GL over 2, this goes, this goes, this goes, this goes, so equals 0. So it seems so initially, if we start it just with that length of string and at that velocity, then we have no downward velocity. Okay, so this is interesting and makes sense. Okay, so rather than just hacking at the equations, why don't we try and learn a bit more from actually looking at the form of this potential. So let us sketch U of f. Okay. So here, okay, here I won't build it up, I will just take what we have on the slide. So this is the, again we have a potential energy as before going upwards. This is the J squared over 2m r squared coming downwards. So we end up with this shape here. Okay, so U of f has this shape there. So we have, again, two possibilities. So we have, this is circular motion if we have an energy there, and then this is a varying radius if we have an energy which is larger. Once more, in all cases we have a bound case. what is very interesting indeed is that whatever the energy you give this system, so you can draw a line here higher and higher and higher and higher, but because this is an asymptote going upwards, the intercept will always be at a radius which is bigger than 0. Okay. Note, all solutions have R minimum greater than 0. So what does this tell us? This tells us that the ball, the ball cannot go through the hole, right? So this is interesting, maybe non-intuitive, but the ball cannot go through the hole. And why is that? That's because angular momentum needs to be conserved. So there's no solutions. Well, we said no solutions. So ball can't go through hole. But this is if there's no friction. And this is a consequence of angular momentum being conserved. So finally, I want to come back to the case of the circular motion, what we analysed before. We just have enough time to do this. Let me go. Let me do it at the analysis here. So let's find a case for circular motion studying the effective potential. So the circular motion solution is when we are at the minimum of the effective potential, right? So let us find this minimum. So du by dr is going to be, in this case, because u of f is j squared over 2mr squared minus mg L minus R. So if I differentiate that, I find we have minus j squared over mr cubed plus mg. So so at 0, this gives us R equals what I call R0. So we have 0 equals minus j squared over mr0 cubed plus mg. So this gives me that R0 equals the cube root of j squared over m squared g. But we know what j is, because that is we know that j is a m v naught L over 2, because we start with a string length of L over 2 on top of the tabletop. And so R0 is equal to the cube root of V naught squared L squared over 4G. But of course, though R0 is giving the radius of the circular motion, it also must be the length at which we start the motion. It is equal to L over 2. So we have that L over 2, let us cube everything, is equal to V naught squared L squared over 4G. So you see I'm proceeding to try and get a solution for V naught. Just a moment, Neville. I actually inherited these lecture notes from him, but this is an embellishment. He didn't go into this detail, much more superficial. So if we solve for V0, we find that it's equal to GL over 2 square rooted. And this is the result which we had previously when we did that simple-minded analysis from the forces. So this is the same result as before. So reassuringly, the analysis of the effective potential has given us an identical result. Okay, let's finish there. And next week we will then analyse planetary motion and orbital motion using Orvis mechanism. So thank you.